Good morning, respected jury and dignified organizers. I'm Sri Krishna Satyajit, and we have today with me Gauri Lakshmi and
Good morning.
Dennis Davis.
Good morning.
Ashwin Jason, he is having a small mic issue. He'll be joining now. And we have Pawan Paul.
Good morning.
And we are Team Hubble. Today, we are going to present our project, Mission GJ667cc. The introduction. The crew. The mission would actually consist of 50 crew members. We have done some approximations and we have come up with the following stats. 3 botanists and 4 biologists for any emergency issues regarding the crop production, 15 engineers for various works, 5 architects for the infrastructure, 5 doctors and 1 surgeon for the welfare of the people, of the crew members, 3 telecommunication system designers for any communication systems, 5 astrophysicists, 4 chemists, and 5 technicians. This would be our 50 crew members. The mission. Our landing craft has been designed in such a way that we will be able to easily dismantle the ship and reuse its materials for future use. The craft will also contain certain essentials like food and materials and water for a few weeks until suitable infrastructure for crop growth is actually made. The landing craft would also be the primary source of shelter and storage in the initial stages. Over to you, Gauri.
Let me introduce our planet Glea 667cc. It is an exoplanet 23 light years away from Earth. Also known as Super Earth, it is one of the most Earth-like planets with 3 times the mass. Residing in a tri-star system, it's in the habitable zone of its star Glea 667c. Glea 667c is a red dwarf. This planet receives 90% of the light Earth does. Since it's tidally locked, one side is always day and the other is always night. But there is a belt separating the zones called the habitable zone, where liquid water is found. However, tidal locking does not severely affect us because GJCC has a thick atmosphere, so the heat is evenly distributed. Over to you, Dennis.
Infrastructure. For the purpose of construction, it is not feasible, practical, to carry tons of iron rods, cement, bricks, etc. into space, and hence we have decided to 3D print all our structures. 3D printing. We would be 3D printing all the structures and resources such as furniture using composite basalt fibers. We have selected 3D printing as it is cost effective, time effective, and it is easy in handling. Moreover, if these structures undergo any structural damage due to physical or climatic conditions, the material used for those structures can be reused for reconstruction of the same without any decrease in its strength. The reason for using composite basalt fibers and not any other commonly used materials such as plastics, metals, and other fibers include 1. The tensile strength. It is 15 times stronger than non-reinforced polymers and 5 times lighter than steel. 2. It is durable and lightweight. 3. It is cost efficient. And lastly, it is abundantly available on the planet due to its rocky surface. The HAB. The HAB stands for the hexagonal array of blocks and will be located in the twilight zone. The name itself implies that the structure will be in the shape of a hexagon. Each HAB will cover an area of approximately 800 to 1000 square feet and can accommodate up to 5 people. The HAB will be dual shelled and will have a total thickness of 15 centimeters and 4 floors. It, along with all other structures, will be both pressure and temperature controlled using in-site motors and cooling equipment procured from the landing craft. There will be 2 types of HABs. The first is to exclusively facilitate accommodation, while the other is exclusively for research purposes. In order to accommodate 50 people, we will have 10 accommodation-only HABs and 5 research-only HABs. We have adopted the hexagonal shape as it can withstand the high winds and stress. One of the major problems faced by astronauts is psychological stress. Constructing a bunker would have added to this stress, considering the fact that such a living situation would resemble a nuclear shelter here on Earth. That is why The hab will be above ground, have windows on all 4 floors, and even a miniature garden and a recreational area. Distribution of land for various projects. We will be dividing the location of our structures among all 3 sides of the planet. The solar panels, the concentrated mirror farm, etc. will be located on the light side of the planet. The ground control station, the biogas plant, and the biohouse, the dark side. And finally, the habs and the windmills in the twilight zone. Also, all the structures in the light side of the planet will be coated with hafnium carbide and lead to ensure protection from extreme temperatures and radiations respectively. The communication towers, satellite antennas, and charging points for communication and transport system respectively will be scattered throughout the planet. Now we have the detailed prototype plan of the Phase 1 infrastructures. 1. The settlement, 500 acres. 2. The solar panel farm, 100 acres. 3. The windmill farm, 100 acres. 4. The powerhouse, 500 acres. 5. The mirror farm, 1,600 acres. 6. The turbine powerhouse, 800 acres. 7. The sub-powerhouse 1, 100 acres. 8. The sub-powerhouse 2, 50 acres. 9. The biohouse, 500 acres. 10. The sub-powerhouse 3, 50 acres. 11. The communication tower and ground control station, 150 acres. 12. The biogas plant, 50 acres. And finally, the water tanks near the biohouse and the concentrated mirror farm, 10 acres. Over to you, Gauri.
Life support. Since the planet is 3 times more massive, we're gonna weigh 3 times as much as we do on Earth. Okay, for this, so because of that, we're gonna be using an exoskeleton. For this, we're going with Guardian Exo by Sarcos. It is a full-powered body exoskeleton. We're using this instead of traditional ones because it has full body support as opposed to only leg support. It can amplify operator strength by 20%. It is battery powered with hot swappable batteries. Get out of the way control system eliminates latency. Hands-free mode allows operator to simultaneously do tasks with their hands while carrying load. We're redesigning the suit to fit our own expeditions. We're going to use an isotope of graphene to build it that's 10 times stronger than steel but much lighter. Because we need the suit to support more weight as we're going to weigh 3 times as much. Over to you, Ashwin.
Good morning. So, communication systems. At the initial stage, we will be using handheld transceivers as the medium for communication. It's basically a portable two-way radio transceiver. So, why did we choose HTs for the job? Well, it's because setting up of a satellite, installing towers and ground station infrastructure, it will consume a lot of time. These HTs can be of very high frequencies, VHF, which are in a bandwidth of 30 MHz to 300 MHz, or UHF, which are in a bandwidth of 300 MHz to 3000 MHz. We are integrating a transponder to all the HTs. These transponders can differentiate the radio waves as they can change frequencies. They also can remove the noise and amplify the signal power. So why did we just not stick into either UHF or VHF? Well, this is because neither one of them is inherently better than the other. VHF can travel more than the UHF. It can also penetrate through objects. But these UHFs and VHFs act differently around structures. The UHF's wavelength is roughly 1.5 feet wide, while the VHF's wavelength is roughly 5 feet wide. Hence, UHF is better to navigate through small places. Using these HTs at VHS, we can communicate at a distance of 45 kilometers at least. This is because Gliese is approximately 3 times bigger than the Earth. As there is an inverse relationship between curvature and radius, that is, the amount of bending of an arc will decrease as the radius increases. Hence, we can communicate at distances like these in Gliese. When we come to antennas, we have to use whip antennas as it's longer because shorter stubby antennas can reduce the range up to 30%. Sri, can you change the slide? For communication while exploring the planet, we can't use old text like Snoopy Cap because it will create problems like having different cap sizes, cannot be adjusted once worn, etc. For solving this in the new communication carrier assembly, we are integrating the microphones and speaker into the suit. We will be using Bluetooth while exploring. that is of electromagnetic waves with 2.4 gigahertz frequency. Why Bluetooth? It's because not only just that we only need to communicate for a short radius, but we can also share data through this. When we come to satellites, we are launching it from space before landing because launching it from the ground will consume too much time and energy. As for transmitters and receivers for this, because we only have one satellite, we cannot go for space networks, space relays where it depends on other satellites to relay data on fixed ground stations. So we do need to position transmitters and receivers on various parts of the planet. Low gain antennas will suffice for this. These satellites will spread their signals in every direction. This will make it easy for them to pick it up rather than at focused areas. Once the initial stage is done, we can switch from HTs to cellular technology. The plan is to have 5 towers initially, and then we can increase this number while developing. When the number of towers increase, we can use techniques like multiplexes. Thank you. Now I'll be switching over to Pavan.
Energy. Energy is something that we need very much in the current generation, especially. Every single device we use requires energy in one or the other way. Sri Krishna, next slide, please. So, in the new planet we are going to, our total power for the project will be 75 megawatts. The total power produced of the proposal is 220 megawatts. For this, the different energy sources that I am using is solar panels, windmills, concentrated solar power, and biomass. Next slide, please. Solar energy. Now let's look on to some advantages of the solar energy. Sustainability with absolutely no harm with the environment. And there's a lot of efficiency by using solar panels, especially in glacier. Glacier consists of tidal locking, which means there is no nighttime loss. And it also has a red star. Now, a red star would be considered a disadvantage with the panels we currently have on Earth, as they cannot absorb energy from an infrared spectrum. But we have used materials like carbon, nitrogen, and oxygen, which are semiconductor polyesters, which is used in the semiconductors, which are known to attract more energy from infrared spectrum. Maintenance is comparatively very low as compared to diesel power plants. Production cost is also very low, as these materials, carbon, nitrogen, and oxygen, are both abundant in Earth and glacier. Now, everything has wear and tear. So eventually we'll have to swap out the panels. Now, swapping out panels is not going to be very much costly, as there are existing printers which can print out these semiconductor polyesters as mentioned above. Moving on to concentrated solar energy. Concentrated solar energy doesn't have much high advantages except for the heat which can be utilized, which is provided by glacier. Now we are going to use this heat to boil water and use the steam to run steam-powered powerhouses. We have used concentrated solar energy just because of its added power source only and its high capabilities of producing high amounts of power. Next slide, please. On to windmills. Now, windmills take good use of wind conditions. As mentioned before, glacier has tidal locking, which results in one hot side and one cool side. At one point or at one region, there is going to be varying wind speeds, which creates high amounts of wind. We are going to utilize this by using windmills. Now, if we use the 5 megawatt existing windmills which are present on Earth, they couldn't handle speeds above 55 miles per hour, which might result in braking. Assuming the wind speeds are going to be twice as much, we are going to use twice as large windmills and more capable windmills, which are 10 megawatt ones, thus resulting us with more power as well. Now, the second advantage of windmills is that it consists of modular parts, so fast and effortless assembling. It is also a reliable source, very less maintenance, and it is built to last in severe climatic conditions. On to biogas. Biogas acts as a waste management system. It provides gas to the settlement area for cooking. Now, biogas can also has more room for expandability to produce hydrogen and in order to use that hydrogen for electricity. But in the initial stages, we are planning to use biogas only as a waste management system. Transport. We humans need to move from one place to another constantly. So we are planning not to repeat the mistakes we have done on Earth by creating roads. Rather, we're going to use means of transport of air. So for the individual purposes, we have formed affiliations with the gravity industries with individual flying suits. And for the mass transport, we have formed affiliations with the Archer Industries with their electronic choppers. We have chosen air transport to get rid of the havocs in smoothing the terrain for the routes. Over to you, Sri Krishna, for the food.
Thank you, Pawan. So food and water. So food and water is actually one of the most important aspects of the colonization. Imagine having a colony without a permanent source of food and water. That would be a life-threatening situation. Therefore, we have come up with certain designs and infrastructural practices for having good amount of food and clean drinking water. The biohouse. Why do we actually require a biohouse? It comes down to 3 points. The first point is the effect of hypergravity on plants. I mean, with the glass being 3 times as more massive than Earth, the gravitational pull would be assumed to be as 3 times more than that of Earth. Therefore, the plants would have many problems faced as one of the problems would be the height of the plants. It will be also showing dwarfism problems and also a lot of hormonal problems. The second one is due to the increased amount of red light emission due to a M category star. We all know that the Gliese 67cc actually orbits a M category red dwarf star, Gliese 67c. Therefore, as the M category is item and in the infrared zone, we actually require plants to actually adapt to those conditions. And third, otherworldly contaminants such as natural chemicals, atmospheric contaminants, and soil nutrients present on the planet. So that's why we require a biohouse. Now we come to the structure. The biohouse would actually take up the shape of a circle, and after complete construction, it would have an approximate radius of 0.6 kilometers. But based on current calculations, the biosphere actually would require 200 days for complete construction. Therefore, we have come up with the modular designs. What is the modular designs, you may ask? The modular designs is actually 100 square meters in area, small modules, which would actually help start production in the beginning stages. So instead of waiting 200 days for the complete biohouse to be constructed and actually waiting 3 more months for the crops to grow, we are actually having a 100 square meter area in the first initial stages, which would also require less energy in the initial stages. Energy. The power requirements for the biohouse after completion is about 50 to 75 megawatts per earth day. And here also the modular design shines its place, as the first module will require very less energy, not even comparable to the 75 megawatts per day ratio, and that would also require, it will also go with infrastructural practices of our minerals, which is actually present in the initial stages. From tilling to harvesting, Rivera AI. So we have actually come up with a fully automated process of automatic harvesting and tilling of the biohouse. We'll be using first 3 stages. The first stage is actually the automatic tilling system. The automatic tilling system, or as we have dubbed it, the tillers, will actually be using we will be using automated robots actually connected to a central AI system. The tillers automatically manage to in specific rows in each flow of the biosphere at each tilling season. The special containers in the robots will also contain the required manure and fertilizers produced by the waste of biogas process and the seeds or buds, which will continue the sowing and the tilling operations into one. The tillers would be approximately 3 feet in diameter, able to row about 6 rows at a time, and approximately 100 of them would be spread at each flow. The next step is the harvesting. Automatic harvesting would be deployed by the central AI system using intricate systems for observation and harvest. The system actually use a system to study these plants and also also have the time from where the crops should harvest. We have also tied up with abundant robotics for this type of infrastructure. Irrigation systems. Pipe. The third one is the irrigation systems, and the pipes will be laid from a reservoir explained before to the dam next to the biohouse. Rivera is the AI system which we have designed for this operation. Rivera, also known as a recreational engineering system for volume analysis and rotation of agriculture, is actually one of the most important part of the biohouse. It is actually a AI deep learning system that will be preloaded into the landing craft's main system using the main computer's database. Rivera will be loaded with sophisticated technologies and agricultural systems to be at maximum efficiency. Rivera will also be providing current information at real time to the botanist at the botany module in the app so that we would be also be capable for problem solving. The main jobs of Rivera, as discussed above, is to harvest, is to till, and also check out the lighting systems. So now we come to the lighting systems, as I said before. With a surface temperature of approximately 277.4 Kelvin and also being tightly locked, we actually need to recreate the daylight cycle on Earth. As plants are actually evolved to have different types of photosynthesis, known as light and dark photosynthesis, on each time of the day. Therefore, we would have accurate lighting systems so that each time of the day would actually be reproduced on Glias 67cc. Thus, this would actually create no problems to the photosynthesis cycle of the plants. Sorry. Now we have biotechnology. Why do we need biotechnology in colonization? It actually comes out to two things: speed breeding and nutrient-rich crops. Speed breeding is described as a technique that manipulates external conditions of plants to increase maturation speeds. Based on current techniques, speed breeding can actually achieve up to 6 generations of spring wheat, barley, and grains in one earth year. And that is based on current techniques. Imagine this in the future. That would actually cut down crop growth times by a vast amount. And then it comes to nutrient-rich crops. The technique of speed breeding actually combined with more nutrient-rich crops will increase the production rates of the biohouse. Imagine eating less for more energy. That's what nutrient-rich crops mean. Now we have also included a segment of bioprinting into our project. What is bioprinting? And the use of cell cultures and cell apparatus to multiply cells and create meat-like objects. This can also be used at medical purposes in case of any in case of any diseases or injuries in the hab. We have actually based this on the technology developed by the Israeli company Aleph Farms Ltd, where cells are normally grown in cultures that are incubated and grown to acquire the original taste of the meat without even growing any animals. We have also used this actually to create more protein-rich foods, as bringing animals to another new planet is very hard, and the payload of the landing craft would be actually huge. Therefore, we have come up with this technique. Now we have the diet of the crew members. The diet we have actually presumed for the colonists will actually be a vegan one. Vegan diets are better as domestication of animals will be tough in early stages, and it's really hard to bring animals towards the planet. We have actually based this on vegan meat, another topic which we are discussing, which uses plant products to create the sensation of meat. A colony will require the happiness of the crew members. Therefore, we also need the happiness of our crew members. That's why we have vegan meat. Vegan meat is actually introduced by a big company known as Beyond Meat, a Los Angeles-based producer of plant-based meat. Next, we come to water. So now we have discussed about the food systems, the food requirements, the crop growth, the crop cycles, everything. But now we come to water, one of the most other important thing. We have as this water is we actually have all these different contaminants on the planet. Therefore, therefore we Therefore, we would be using forward osmosis biomimetic membrane technology, which will be used to filter water on Glias 667cc. This technology could also be used in the landing craft to filter water. What is forward osmosis biomimetic membrane technology? It actually uses aquaporin membranes to filter water, which is way more efficient than cellulose-based membranes. Aquaporins are crucial for all life and organisms, from bacteria via plants to man. They also facilitate rapid, highly selective water transport across the membranes. This technology is actually based on a European Space Agency test done in September 2015 to remove substances from. Thank you.